Can I get some water here? You may have noticed that John announced a title which was rather different from the title on the poster. When I originally gave that title, it was rather more technical. I didn't realize that this was meant to be a colloquium style presentation, so this will be less technical than that previous title hinted at. I'll be very happy to discuss more of the nitty-gritty and technical aspects of these areas in private afterwards. I'll be here all afternoon. But for here, I'm going to talk about Majorana and Majorana fermions in a way that I hope will be accessible to a wide audience. There aren't very many romantic stories in physics, but the story of Majorana is one of them. So Majorana lived a short life, or at least was known only to the physics world only during a short period. But he made a great impression. This is what a famous scientist said about Majorana. There are many categories of scientists, people of the second and third rank, who do not do their best but do not go very far. There are also people of first-class rank who make great discoveries fundamental to the development of science. But then there are the geniuses like Galileo and Newton. Well, Ettore Majorana was one of those. And the person who said this was someone who was not given to extravagant statements, especially extravagant praise. Enrico Fermi, who knew Majorana quite well. Majorana's most famous work is a 1937 paper containing results he derived several years before. And in fact, the story is that he had to be persuaded by Fermi to write the paper. And in fact, that Fermi wrote significant parts of that paper for him. On the 27th of March, 1938, Majorana boarded a steamer from Palermo to Naples, and he was never seen again. And there are various stories and conjectures about what might have happened, but that's the romance of Ettore Majorana. He's become a mysterious presence or absence, but his work very much lives on. So I'm going to discuss one aspect of his work, the concept of a Majorana fermion, which reverberates further and further as time goes on throughout modern physics. So in 1928, Dirac proposed his relativistic equation for electrons, the famous Dirac equation, so famous that it appears on the wall here. The Dirac equation was a watershed in theoretical physics, led to a new understanding of spin, predicted antimatter, and its interpretation, which was problematic at first, inspired the development of quantum field theory, made quantum field theory necessary, because as an equation for a single particle, the Dirac equation did not make sense. It had well-known problems with negative energy solutions. That's what I like to show what people looked like. This is what Dirac looked like about the time of the Dirac equation. And this was the discovery of the anti-electron, which came out of the interpretation of Dirac's equations as a prediction. This remarkable development out of the Dirac equation inaugurated a new method in theoretical physics emphasizing mathematical aesthetics. Dirac had gotten his equation by attempting to get an equation for the electron that generalized Schrodinger's equation. Schrodinger's equation was not invariant under relativity. It was a non-relativistic equation. Dirac wanted a relativistic equation that led him to something quite new. And the mathematical elegance of that construction inspired this new method of theoretical physics of guessing equations by demanding symmetry and mathematical elegance and coherence. Well, Majorana out-Dirac'd Dirac. He asked an even more kind of gratuitous question. I mean, reconciling special relativity and quantum mechanics was not gratuitous. That's something you needed to do intellectually and experimentally for atomic physics. Majorana's construction was much more a free invention of the human mind. The photon is a neutral spin-1 particle. That's its own antiparticle. And those facts can be used with modern technology to get the essence of Maxwell's equations. Maxwell's equations are the description of the kinematic description of a massless spin-1 particle. That's its own antiparticle. Majorana asked if there could be a spin-1/2 version. So more specifically, Majorana asked if there could be a modified version of the Dirac equation which would be suitable for describing electron-like particles that are their own antiparticles. Let me discuss it at a little more technical level. Dirac's equation connects the four components of a field psi, and in modern notation looks like this, with partial derivatives, gamma matrix, and a wave function psi. The gamma matrices are required to obey the rules of Clifford algebra, so their anti-commutators reproduce twice the metric, or more explicitly, one of them squares to 1, the other three square to -1, and they anti-commute. Dirac, in his original presentation, postulated a representation of those gamma matrices that involves both real and imaginary numbers. Then, in order for the Dirac equation to make sense, the psi field has to be complex. It has to have both real and imaginary parts, because the equation mixes real and imaginary up. Dirac and others regarded this as a good feature because electrons are charged particles. I got it. All right, thank you. Dirac actually regarded this as a good feature, as did others, because electrons are charged, and charged particles require complex fields, even at the level of the Schrödinger equation. In fact, Dirac thought of this as a prediction that the electron should be charged from the possibility of getting a consistent relativistic equation. So he's not only predicting the existence of antimatter, but also the existence of electric charge for electrons. Another perspective is that in quantum field theory, psi destroys electrons and creates positrons, while its complex conjugate does the opposite, and so they have to be distinct when we pass to quantum field theory and operators instead of numerical wave functions. Even more specifically, then what Majorana asked himself was, can there be an equation of Dirac's type that works for a field with psi star equal to psi? So you could have spin 1/2 particles that are their own antiparticles, analogous to how the photon is its own antiparticle. For this, we have to have, if you go back to the Dirac equation, where I gamma times partial derivatives is equal to acting on psi is equal to m psi, you have to have the gamma matrices being pure imaginary, but they still have to satisfy the Clifford algebra. So the central result of Majorana's paper as mathematics is that he found a set of gamma matrices like that, gamma matrices that satisfy the appropriate squaring and anti-commutation relations, but are entirely imaginary. And there they are, in tensor notation as 4 by 4, and here they are really spelled out just as matrices. This is out of order. Let me skip that. So that's the background and really the content, the main content of Dirac's 1937 paper, although he actually, it's of historical interest that in that same paper he formulates an action principle that gives the Majorana equation, and notices that for that action principle to make sense, he needs to use anti-commuting fields. So that's the first appearance that I know of Grassmann variables in quantum theory. Nowadays, of course, they're everywhere. So, returning to a question of physics, Majorana was a very down-to-earth physicist as well as a visionary. Most of his papers are about applied questions in atomic physics. He speculated that his equations might apply to neutrinos. In 1937, when this paper appeared, neutrinos were still very hypothetical particles with totally unknown with many unknown properties. They finally were discovered in 1956 as experimental entities, but their properties appeared to disfavor Majorana's concept that neutrinos might be their own antiparticles. Specifically, there seemed to be a strict distinction between neutrinos and antineutrinos. The distinction is connected with the laws of lepton number conservation, so let me quickly review what those are. I put these in scare quotes because we're going to deny these laws pretty shortly. But the approximate law of electron number conservation says that in any reaction, if you count before and after the quantity number of electrons minus number of anti-electrons plus number of electron neutrinos minus number of antineutrinos, that's the electron lepton number, that should remain constant. It should be the same before and after. And there are similar laws for muon and tau number. Now, of course, if neutrinos are really different from antineutrinos, they can't be Majorana particles, and if they're contributing with opposite sign to the laws of lepton number conservation, they're definitely different. There seemed to be a lot of experimental evidence for these laws. However, in recent years, the situation has come to seem less clear-cut. It's been discovered that neutrinos oscillate. In some sense, this is a small effect, but neutrinos can travel a long way, and they have time to do rare things. And the neutrino oscillations indicate that at best, only the sum is strictly conserved. Actually, I'm sorry. I was missing some slide. Somehow this got jumbled. I should have discussed, I dropped the slides that showed us the illusion of these laws. So let me play it. Shouldn't spoil the show by making it seem too easy that these laws disappeared. So what were the kind of evidence for these laws? People won Nobel Prizes for these things. In fact, for experiments at Brookhaven. So the kind of observation that led people for a long time to believe in these laws, that there was a distinction between neutrinos and antineutrinos, are things like this. If you look at the neutrinos from pi plus decay, so pi plus goes to a muon plus some particle, we'll call it the neutrino, muon neutrino, then that particle, according to the law of muon lepton number conservation, is capable of turning a neutron into a proton because it produces a muon here, not an anti-muon, and so muon number is conserved. Whereas this one, sort of the cross reaction, is not possible, doesn't go, because this would violate the law of lepton number. Nothing else forbids it. If neutrinos were the same as antineutrinos, in fact, this would happen. And in fact, if you look at the particles that accompany pi minus decay, which are antineutrinos, they induce this interaction. So this is one of many, many observations that led people to believe in the law of lepton number conservation. Okay. Sorry about that glitch. But if you let your muons, your neutrinos travel a long, long way, your muon neutrinos travel a long, long way, it turns out that they can become electron neutrinos or tau neutrinos. And these separate conservation laws for the different kinds of neutrinos has been overthrown experimentally. It's not clear from an experimental point of view whether the sum of the lepton numbers is strictly conserved. By looking at different reactions, you can see that electron neutrinos can turn into muon neutrinos can turn electron neutrinos. Every neutrino type can turn into any other neutrino type. Any antineutrino type can turn into any other antineutrino type if you let them propagate long enough. But so far, the question of whether neutrinos can turn into antineutrinos is unsettled. But neutrinos, just the existence of oscillations poses a theoretical question. Something has to set the scale for how rapid these oscillations are. And that is the mass of the neutrinos. So the existence of oscillations tells you that neutrinos have non-zero mass. Another way of thinking about it is going back to the Dirac equation, which is the equation for how spin 1/2 particles propagate. Neutrino oscillations mean you should use, instead of in the place of that m, you should use a matrix which encodes the possibility of one neutrino changing into another, and that's how we capture the possibility of oscillations in equations. So, if electrons have mass, then the concept that they're purely left-handed or purely right-handed goes away. If you have particles that are zero mass, they can be moving along, and if they're spinning with their axis of rotation in the direction that matches your left hand moving along, they're called left-handed. If it's this way, they're called right-handed. If you have a particle with non-zero mass, you can move so fast that you overtake it, reversing in effect the direction of motion, and that would change a left-handed thing into a right-handed thing. And therefore, you can't have laws consistent with the theory of relativity that make strict distinctions between left-handed and right-handed objects. So neutrinos, which were in the days when neutrinos were thought to be massless, were thought to be entirely left-handed, can't be entirely left-handed. They have to have an admixture that's proportional to the mass and inversely proportional to the energy of right-handed kinematics. So, awakened from our dogmatic slumber that there's all these distinctions among neutrinos, we can reopen Majorana, and now knowing that neutrinos have to be massive, we can reopen Majorana's question: could the apparent distinction between neutrino and antineutrino be superficial? The morning and the evening star appear to be quite different, but we now know that they're both Venus, seen in different circumstances. And in particular, we can entertain the hypothesis that the right-handed neutrino and the left-handed neutrino, which were thought to be distinct, that is, the left-handed particles are always neutrinos and the right-handed particles are always antineutrinos, we can ask ourselves, since there has to be a kinematic admixture between them, whether the kinematic admixture really has to be something new and entirely different, or whether the small kinematic admixture that we need for relativity in the neutrino could be the good old antineutrino. That would not be inconsistent with the laws of lepton number being accurate to a high degree of accuracy, because the admixture, being m over e, is very small for practical energies. Considering that more carefully, how can nu equals anti-nu, Majorana's idea that neutrinos are their own antiparticles, be reconciled with the many observations which tend to seem to indicate they're different? The point is that the particles produced in a decay like pi plus are in a very different state of motion from the particles produced in the decays of pi minus. Experiments show that in the first case they're almost entirely left-handed. In the second case they're almost entirely right-handed. And so the idea is maybe that's the distinction between neutrinos and antineutrinos. They're not intrinsically different particles, they're just the same particle in different states of motion. And the reason that they interact so different, they look so different, is that the weak interaction is very strongly spin dependent. So logically, the neutrino and antineutrino might be the same particle seen in different states of motion. Now, if you could bring neutrinos to rest and do experiments with neutrinos at rest, it would be very simple to test this hypothesis. You could see whether neutrinos and antineutrinos behave the same way. In particular, you could slow down two neutrinos and see if they annihilate. If they're particle and antiparticle, they should be able to annihilate into nothing at all. So that would be the ideal way to see if neutrinos are their own antiparticles and settle this question of whether Majorana was right, but it's not practical. Neutrinos are difficult to slow down and study, even though we think on very firm grounds that analogous to the microwave background of photons that's left over from the early universe, there should be a microwave background of very, very slowly moving neutrinos. So they're there, they're all around us, hundreds of them in every cubic centimeter. But they interact so feebly that experimental physics has not risen to the challenge of detecting them at all, much less seeing whether they annihilate. Several other kinds of experiments are underway to test the conservation of lepton number, total lepton number, which is the remaining barrier to the idea that neutrinos are the same as antineutrinos. The most sensitive are searches for neutrinoless double beta decay. If lepton number is violated, it's possible for a germanium-76 nucleus to decay into selenium-76 plus 2 electrons. It's known that this decay can occur if you have not only 2 electrons, but in addition 2 electron antineutrinos. The phase space for the interaction is very small, so if this reaction is possible, it would be kinematically very favorable to do it. And so this is a sensitive way to look for tiny effects of lepton number violation. Unfortunately, so far, there's no positive result, despite many millions of dollars, many tens or hundreds of millions of dollars being spent on this and similar kinds of experiments. And the search continues. There are some claims of positive results, but they're not widely accepted. What?
Hans Platform.
Yes, well, that's, I don't know if this first name is Hans, but well, if you say so. Meanwhile, the leading theory of neutrino masses, which is rooted in ideas of unified field theories, predicts that neutrinos are Majorana particles. So some very major theoretical issues about the unification of forces hinge on this question. Let me move on to another area where Majorana neutrinos have become very important. And although it's a much newer area, this one might well break through earlier and on many more fronts than neutrinos. There are good reasons to expect that broken supersymmetry is a feature of our world, with some of the superpartners at least weighing in at less than a TeV. I'll try to convince you momentarily. If so, they should be discovered at the LHC in the next few years. So let me make the case very briefly, but I think powerfully. The standard model as it comes can be summarized on one transparency, and there it is. It has the strong electromagnetic and weak interactions. It has an elegant description of matter and the interactions being non-abelian gauge theories based on these symmetry principles and these multiplets and the assigned charges for the U1s. And really, that's all you need to know to make an honest reconstruction of most of the standard model. And it would be difficult to overstate the power and success of this model as a description of nature. So this is close to God's last word. Yeah, where there's 3 families, and there are also Higgs particles. That's coming. But it's not as given that it's close to the last word, it's not as perhaps as elegant as it should be. There are 3 fundamental forces, and that's more than one. There's also gravity, which has been left out. There are 6 fundamental materials. Within the quarks of different colors, and one-handedness should not be regarded as different particles. They're really the same particle viewed from different perspectives. and so forth, but the symmetries, the gauge symmetries, which identify the particles in their essence, do not make relations among these 6 different kinds of entities. So we need 6 fundamental materials, plus the 2 repeats to make the different flavors. And plus now there's the Higgs particle. So given the amount of data and reality that it describes, it's very impressive, but just because it's close to the last word, we should hold it to very high standards. And by the highest standards, 3 is greater than 1, 4 is even more greater than 1, 6 is definitely more than 1, and 6 times 3 is a lot less than 1. So it's not as unified as it could be. We can go a long way towards making it unified if we systematically look for how those forces based on symmetry can be integrated into a larger symmetry. And as the mathematicians in this audience don't need to be told, the possibilities for low dimension, low rank Lie groups are very small, so the possibilities for embedding standard model symmetries in larger unification schemes are quite limited, and so it's not automatic that it'll work. But SU3 cross SU2 cross U1, the standard model fits very snugly into SO10, and even more impressively, those 6 different kinds of materials snap into place into one irreducible representation, so they all become one material, the spinor representation for experts of SO10, 16-dimensional spinor. So all that structure that I showed before of the 6 multiplets forming in exactly the pattern they do with the strong electromagnetic and weak interactions falls out with this identification. If I didn't know the names of these particles or their properties, I could reconstruct them from this theory of SO10. The different colors in the spinor representation are different charges, colored charges, weak charges, and all the different assignments follow from the idea that we have possibilities of plus or minus charge for each of those colors. That's subject to the restriction that the number of plus signs is even. And even more impressive, the funny hypercharges, the U1s, which were necessary in order to reproduce the electric charges of the particles, and which were just phenomenological parameters within the standard model and had funny values like 1/6 and -1/3. Those are now consequences of their other strong and weak properties. So it all makes a nice package. Won't attempt to do justice to all the details, but take my word for it. So now we have just one material and one force. It's progress. We still have to multiply by 3. And we still have the Higgs particle. But we've done a lot better as far as forces and materials are concerned. Coincidence? I think not. In this unification scheme, the light neutrino, as I mentioned before, is its own antiparticle, as is the heavy Majorana. Both the light and the heavy are Majorana neutrinos. There's even evidence, experimental evidence, numerical evidence, that this unification is on the right track. Here is the failure of the theory, taken at face value. If we can calculate whether the different observed couplings at relatively modest energies, when we extrapolate and correct for vacuum polarization effects, unify at a much shorter distance or higher energy, where we'd expect simplicity to emerge, and the theory predicts simplicity and unification to emerge. If we just use the particles of the standard model, it almost but not quite works. So this wonderful idea that we could unify the matter, unify the forces, seems tantalizing and successful at the level of quantum numbers and almost numerically, but not quite there. Now, if we were disciples of the philosopher Karl Popper, who taught us the goal of science is to produce falsifiable theories, we could pat ourselves on the back at this point, having produced a theory that's not only falsifiable, but even false. But naturally, real scientists don't behave that way. When we're getting close, we are encouraged to think that maybe we're almost there, but just have left something out. And how can we do better in this unification? Well, the unification still leaves us with two things. So the way we could hope to do better is to make just one thing. And in the early 1970s, that would have seemed to be totally impossible and outrageous, because force kinds of particles, photons and gluons, bosons, if you like, with spin 1, seem to be hopelessly different from electrons and quarks, which are fermions with spin 1/2. They have very, very different basic physical properties, like their quantum statistics, not to mention their spin. So we need an extension of relativity that brings in quantum mechanics in a very profound way in order to say, in any sense, that the photon could be the same kind of thing as the electron. Well, I'm not going to recite the full story of supersymmetry here, just to say that if you want to incorporate that potential unification of the different kinds of particles, just as Dirac, in order to incorporate special relativity, had to expand the Schrödinger equation so that it had more stuff, just as Maxwell, in order to make the equations of electromagnetism consistent in his time, had to add new terms from which more stuff emerged. In order to make supersymmetry consistent, you have to add more stuff to your equations. For that matter, in order to make unification consistent, you had to add more stuff. And if you do that, in the case of, you have to correct for the effects of that stuff, which brings in new vacuum polarization, and that curve, those curves that I showed you before of the extrapolated values of the different coupling constants, which didn't quite match, then they match within the experimental and theoretical uncertainties indicated by the width of these lines. Now the extrapolation works. And as a bonus, that didn't have to happen, but is like a gift from heaven. Gravity, which at atomic distances is hopelessly weaker than the other interactions, and so much so that we entirely ignore it when we consider what's happening at the LHC, for instance, or in atomic and molecular physics or chemistry. It's not as the difference between the strong and electric forces is about a factor of 10, but 10 times 10 times 10 times 10. It's 41 orders of magnitude weaker than the other forces at those kinds of distances. However, whereas the evolution of the strong, weak, and electromagnetic couplings due to quantum effects is logarithmic, the gravity interaction in general relativity responds directly to energy. So if we probe it at higher and higher energies, its strength increases very rapidly. Its inverse strength, which I plotted here to make these look like straight lines on a logarithmic scale, goes very dramatically downwards. And from far outside the universe where it started, and so you can't see that part that I plotted, it races down and unifies with the other interactions. So that gives, I think, very strong encouragement to the idea that supersymmetry is a correct part of the description of nature. It really makes unification work, as well as being attractive aesthetically. If it's true, then we have spin 1/2 partners, the unified supersymmetric versions of all the particles that are currently known. So with the photon, we'll have a photino. With the Z boson, we'll have a Xeno. With gluons, we'll have gluinos. These are all spin 1/2 particles that have the same kinds of quantum numbers as their spin 1 analogs. And therefore, they're all their own antiparticles. Just as the photon is its own antiparticle, the gluons are their own antiparticles. These additional things that we need in supersymmetry will all be their own antiparticles. So they're all of them. Every single one of them is a Majorana fermion. Among them, one of them, if could be stable and could be produced in the Big Bang roughly enough to make the dark matter, so it's a prime candidate to be the dark matter. So, in any case, if low energy, so it might be that a very large fraction of the mass in the universe is Majorana fermions. But in any case, if supersymmetry is correct and these ideas about unification quantitatively are on the right track, the LHC will provide many realizations of Majorana's idea. Finally, let me discuss one other version of Majorana's idea that's quite different, but also very exciting and I think quite fruitful, or likely to be very fruitful in the future. In his great work, Nambu perceived an analogy between the phenomena that an energy gap opens in superconductivity, which is a sort of mass for the quasi-particles in a superconductor, and the spontaneous generation of mass in relativistic quantum field theory. That's an important element of the standard model. Now, I want to add the observation, a kind of special footnote to Nambu's original work, going back to it, that the mass that he got for fermions in a superconductor, or the mass he was thinking about, is actually a Majorana mass. So inside a superconductor, electrons are Majorana fermions. Well, this is a little bit for experts, but I'll go through it. The basic thing in a superconductor is you start with an electron-electron interaction. So at the level of Lagrangian, you have the possibility of an electron, anti-electron scattering into another electron, two electrons scattering into two other electrons. That's what's mediated by this kind of interaction. Now, in a superconductor, what happens is that Cooper pairs condense, so you have the possibility of these electrons forming a bound state and those Cooper pairs have effectively zero energy cost in a superconductor, so they condense, and therefore you have a vacuum expectation value, a condensate of electrons and also of anti-electrons. Putting in that condensate, you find that this interaction term becomes something like this, which looks like a mass term for the electrons, but a mass term of a peculiar kind where electron number is violated. So it's, if you think about an electron propagating along, this interaction means that an electron, as it propagates along, turns into an anti-electron. That's why we call it a Majorana mass. Let me say this again, now in italics. Inside a superconductor, electrons are Majorana fermions. That may sound shocking because electrons are famous for having electric charge. And this is almost the opposite of what Majorana was trying to do, to explain that you didn't have to have electric charge associated with spin 1/2 particles. And of course, if a particle has electric charge, it's definitely different from its antiparticle, which has the opposite electric charge. So how can it be possible that in a superconductor electrons are Majorana particles? The point is that inside a superconductor, charge is not a good quantum number. You're awash in this sea of Cooper pairs, which is electrically charged. Another way of putting it is you have zero mass Cooper pairs all around you. You're an electron. You grab a Cooper pair of anti-electrons and an electron plus 2 anti-electrons looks like an anti-electron. There's no distinction between electron and an anti-electron in a superconductor. We can actually, so Majorana fermions definitely exist in superconductors, and there's an interesting phenomenology associated with that. But even more interesting is something called Majorana modes. Majorana modes are 0 plus 1 dimensional massless fermions that attach to special points or special objects in materials. So this is a very, very special kind of Majorana fermion, 0 plus 1 dimensional, so it doesn't propagate, it's attached to points, but also massless. So it's a kind of extra quantum number attached to special points, a special kind of object that doesn't propagate, but means you can have degenerate fermion and boson states depending on whether that fermion is present or not. Since they have zero energy, and since they're very small, namely zero-dimensional, it seems appropriate to call them Majorinos, and that's what I'm doing. In superconductors, because of the omnipresent condensate of electron pairs, one can have Majorinos, and in fact, the hunt for them is on experimentally. A hole can and look like a particle, as I mentioned before, in the opposite direction. How do we describe these things mathematically? This is elegant, and I don't want to skip it, but it's a little more advanced. We can't count the number of electrons, but we can keep track of even and odd. So if we're going to make an effective theory that describes the low energy dynamics of this system that contains a number of Majorinos, and we'll keep track of the excitations, the very, very low energy excitations associated with creating and destroying those. If we really want to do justice to that dynamics, we have to incorporate a certain algebra. We have to build in the possibility that electron number modulo 2 is conserved, so we need an operator that does that. That will anti-commute with the Majorino creation and destruction operators, because these change the electron number by 1, or between even and odd. We can't tell what it is modulo 2, but even and odd we can tell. It'll commute with the Hamiltonian and square to 1. So, as I mentioned, and it would take us quite a while to explain, to do justice to, a big effort in condensed matter physics is underway to create these Majorinos in real-life circuitry. I'll assume that that's solved and go to the next step of trying to use these things in circuits by, for instance, consider putting several wires together and such that each of those wires has a Majorino on it, and seeing whether the Majorino survives, or we have a composite object. So if we consider a junction of 5 wires and construct the excitations associated with all 5 of them, we have this object whose algebra tells us that it creates 0 energy excitations, commutes with the Hamiltonian, and anti-commutes with the electron number, with -1 to the electron number, because there are 5, and 5 is an odd number. So the result is that this gamma creates a new composite Majorino. Summation n squares to 1 commutes with the Hamiltonian, and very important, it's not a function of the Hamiltonian, since it anti-commutes with a non-trivial with something that the Hamiltonian commutes with, and therefore it creates a new state that's degenerate with the old state, degenerate with the vacuum that it creates 0 energy excitations from any given state. Okay. It commutes with the Hamiltonian, so no matter what state you have, you act with this thing, you get a 0 energy excitation. So there's a doubling of the whole spectrum. Well, this construction is just giving you a little taste of what happens when you have Majorinos. They obey a very rich and definite algebraic structure that survives all interactions and has direct physical implications. The energy spectrum is doubled, not only for the ground state, but for all states.
But you could have not 5, but 9 or so.
Any odd number would work, right?
Not doubling, it's much more.
Yes, right. So let me. I feel like I'm discussing the tip of an iceberg here. Well, but.
You said Kramers.
What's that?
You said Kramers, but
That is 2.
Yeah, Kramers is peanuts compared to this. This is I've only shown a kind of toy example. What I wanted to show is the power of this algebra in a very simple circumstance. But I won't be able to do justice to it because it requires more machinery. This was just a self-contained example of the power of this kind of algebra. If you extend it, you can start to design circuits. You can start to do manipulations and see, move these Majorana particles around by changing the Hamiltonian. Do for this kind of exotic quantum system what people like Steinmetz did for electrical circuits. You can design complicated systems that embody quantum mechanics in a very and quantum mechanical robustness in a quantum mechanical effects of that I'll describe momentarily in a very robust way, because all the crucial elements are dictated by this algebra and symmetry. But so, as you were saying, if we have several Majorinos, so several junctions, we can have a huge Hilbert space, because at every one of those junctions we have a doubling. So if we have n of them, we have 2 to the n states in the Hilbert space, and a very precise algebraic control of how those states will behave. Because they're in a huge Hilbert space, the wave function can have lots of structure, and we can keep their wave function, it turns out, keeps track not only of where they are, but also of where they've been when you manipulate. So moving them around gives us a powerful way of playing with knots, or actually braids, because we can keep track of where they've been. Their wave function keeps track for us of where they've been, and then since we know theoretically what the wave function is doing, we can even read out the results. So we can follow now in the quantum world the strategy of the Maya for doing mathematical computations with knots. Oh, the Incas, I'm sorry, right. Yeah. The Incas. In a modern incarnation, this is known as knot theory in the braid group. And it's known that you can do very powerful quantum computations with them. And it's also a very beautiful subject. So these observations that you can have precise, robust algebraic control of complex quantum mechanical systems based on basic symmetry principles inspires the vision of topological quantum computing, and it's all based on the existence of these very special kinds of Majorinos that people are on the verge of realizing if they haven't realized them. I went to a workshop last summer at Erice about this subject with a lot of experimentalists, and there were several groups that were claiming that they had done observations, that they had evidence for these Majorinos with some of their properties. And each group, to me, seemed very convincing, but each group was heavily critical of the others. So my interpretation of this is that before long, the situation will mature, and probably all of them are right, but they need to clean up their act to be really convincing. Okay, so in conclusion, I hope I've convinced you that Ettore Majorana's seemingly esoteric question, and seemingly kind of a purely intellectual question, can I make a version of the Dirac equation that uses only real numbers, or has solutions that allows particles to be their antiparticles, which is the physical version, has become central to several promising frontiers of physics. Neutrinos, where the question of whether the neutrinos we love and know and love and thought we understood for a long time are secretly their own antiparticles. In supersymmetry, where we definitely need Majorana fermions in order to implement supersymmetry, and one of them could very plausibly supply the dark matter of the universe. And now inside superconductors, we already have Majorana fermions, unrecognized. They've been there for all these years. But the Majorinos, the zero mass ones that we can really manipulate and control, and that could very well enable the vision of quantum computing. Each of these is an area where I think we're on the verge of great experimental discoveries that will finally bring to fruition Majorana's vision. Will one or more of these break through? I think the question is not if, but when. Okay, thank you.
How is assembling Majorinos different from assembling a speech? You also have an exponential dimensional field space in size.
Well, but these are massless excitations. So this is a huge degeneracy of the ground state. So that's something quite different. Yeah. Certainly you can get very large dimensional Hilbert spaces. If you're not careful, you always get very large dimensional Hilbert spaces. But if you want to have experimental control and things that you can manipulate with delicate instruments and things like external fields, so you can't apply a lot of energy into a small space. If you want control, it's very important that you have low energy excitations involved and deal with a narrow space.
Your talk was announced also to talk about neutrinos, but I didn't hear a word about neutrinos.
No, neuterons. Neuterons. The main thing I like about neuterons is the name. And neutrons seem to be very different from antineutrons. Right? If you put together a neutron and an antineutron, they go up in smoke. If you put together two neutrons, they don't. However, it's theoretically possible and does occur in unified theories at some level, where baryon number is not conserved, that neutrons can oscillate into antineutrons. So that means they're not really different particles. They would also, so properly speaking, if you really want to be precise, the eigenstates of the Hamiltonian, the things with definite mass, in that case, are mixtures of neutrons and antineutrons. So if you look at the spectrum, the actual eigenstates, and real is a little pun there, the actual eigenstates of the Hamiltonian are not a neutron and an antineutron, but a state which is basically neutron plus antineutron divided by square root of 2, and neutron minus antineutron divided by square root of 2. Those have slightly different energies. And that's why if you start with a neutron, which is the sum of the two, and wait a long, long time, they oscillate with slightly different things. Eventually there's a beat, and the neutron is turned into an antineutron. Okay. But that means the real particles that have definite mass are their own antiparticles. They're the neutron plus antineutron or the neutron minus antineutron. And since they no longer have a sex, we can call them neuterons. That the whole point of it. So it could be that the neutrons which we know and love are actually coherent superposition, properly thought of as coherent superpositions of these neutrons. And that brings up a whole story, which maybe is more appropriate to discuss in private, that the distinction between a Majorana particle, but nevertheless, I mean, it would be quite absurd to a physicist to claim that a neutron is a Majorana particle. Because for most purposes, what's important is not that which one is the exact mass eigenstate, but which one has simple reproducible properties in its interaction with the external world. And neutrons and antineutrons behave quite differently in their interaction with the external world. So that's one example of a general lesson, which is that Majorana-ness, that is, whether a particle is its own antiparticle, shouldn't be thought of as a binary predicate. That's either true or false. Things can be more or less equal to their own antiparticles, depending on how you look and the kinematic circumstances. And so, for instance, I also made what should have been a shocking statement, that electrons can be Majorana fermions. And that corresponds to definite physical reality, but it only applies in very special circumstances where the electrons are in superconductors, and in the superconductor where the electron states we're talking about are ones that are very close to the nominal Fermi fields. So particles, things can be more or less Majorana, I guess. If you think about it. Yeah.
Very naively, these Neutrinos in circuits,
Yes.
they don't carry any charge. In a circuit, how do you manipulate them? You can't apply fields because they don't respond.
Well, they're made out of electrons, so you kind of have to massage the electrons that surround them and push that along. They're also, well, the details are under construction, I guess. So, but the algebra is there, and the model Hamiltonians are very explicit, and the relevant information is all there. But it'll be quite an adventure technologically to actually implement these things. Basically the tools you have are electric and magnetic fields, and that's enough to do things if you orchestrate it in the correct way.
Oh, very small. What is a good reference? There's always. Did he write
For which?
Majorana's paper? Is it? There's only one paper.
There's only one paper. His collected works is very slim. I think it's 9 physics papers, of which only 3 or 4 are real interest anymore.
So it's only that paper.
It's a very brief paper. I will say one more thing about Majorana, though. There's a very famous formula for non-adiabatic response called the Landau-Xena formula.
You do Majorana?
Majorana not only derived it, but derived it in a much more elegant and powerful way that's subject to
Versions cannot be true.
generalization. Yeah, it's really very unfair. But even more so because Landau got the answer wrong. That's another story. All right.
Let's thank Frank.
Okay.
Oh.